This conference will now be recorded.
So, good evening. Today, we'll be discussing the limitations of wave theory to explain the general observations we have seen in photoelectric effect in the last class. So, let me just make it a slideshow. So, today's topic will be to discuss how wave theory failed to explain the photoelectric effect, or in fact the observations we see in photoelectric effect, and then how Einstein's photoelectric equation or Einstein's explanation with the quantum nature of radiation helped us to understand and explain the photoelectric effect. So first let me recap the general observations of the photoelectric effect. Then I'll go to the limitations, and then we'll finally understand the phenomenon of photoelectric effect by the use of Einstein's photoelectric equation. So look, this is the experimental arrangement. I'm not going to discuss today because we had already discussed in the previous class. So the basically what is photoelectric effect? If we irradiate a metal surface, here UV ray is shown, but not always UV ray, various rays for various metal surface. If we irradiate with some radiation, then emission of electrons happens from the metal surface. So this phenomenon is called photoelectric effect. And we had seen there are certain features of this experiment. In fact, some specific results we have seen. I'll discuss those things one by one first for the recapitulation. See, for a given photosensitive material and frequency of incident radiation above threshold frequency, the photoelectric current is directly proportional to the intensity of the incident radiation. So we have seen that you can look this thing, that this is the photoelectric current and this is the intensity of the light. Okay, intensity of the incident light on the metal surface. So as you can see from here, that the intensity of light and the photocurrent, they are actually related, like linearly proportional to each other. So photocurrent, if I say photocurrent is directly proportional to intensity of the light. So this is what the first observation, like first and foremost observation we have seen. Okay. Then what is the second observation we see? For a given photosensitive material and frequency of incident light or incident radiation, saturation current is found to be proportional to the intensity of the incident radiation, whereas stopping potential is independent of its intensity. So Deepa has arrived now. Deepa, today what we are going to discuss, in the last class, I think you were there, we had discussed the experimental observations. Look here in the first slide, experimental observations we have seen for photoelectric effect, and we have collected few, like some important observations. So which I say here, overall observations of the experimental fact of photoelectric effect, and those are now I'm just recapping for yourself. And what we'll do today, we'll see how wave theory, classical wave theory, that is electromagnetic theory of light, could not, classical electromagnetic theory of light, where we assume that light is in a wave. So that theory could not explain the photoelectric effect, the observations of this photoelectric effect. Whereas Einstein actually borrowed the idea, quantum idea of radiation from Planck's idea, okay? And then he used it to explain the photoelectric effect. In fact, the observations of the photoelectric effect, experimental observations of the photoelectric effect, and see, we'll just discuss first limitations of the wave theory, then we'll go to learn how Einstein's photoelectric equation could solve or could explain all the observations. So first observations we have seen that photoelectric current and intensity of light, they are directly proportional. That means if you increase the intensity, we are getting more current. So that is first observation. Then second observation was that for a given sensitive photosensitive material and frequency of incident radiation, saturation current saturation current was proportional to the intensity of the incident radiation, whereas the stopping potential, or in other words we can say the maximum kinetic energy, was not depending on intensity, it was independent of intensity. You can look this figure. So look, in this case, I3, I2 and I1, they are different intensities of the light used. So I3 is greatest in having greatest intensity, so that's why the saturation current is the largest. Then I2, so saturation current for I2 is this one, second largest, and this is the least, I1, and the intensity also is in the decreasing order like this. Okay, so we can see that the saturation currents depend on incident like intensity of the incident radiation, whereas the frequency, sorry, yeah, stopping potential where the like stopping potential, what is stopping potential? Stopping potential is actually the retarding so the minimum retarding potential which makes the photoelectric current zero. Okay, so that is called actually stopping potential. And interestingly, we have seen that this stopping potential or the maximum kinetic energy does not depend on intensity of the light. Then let us go to the third observation and fourth observation. So third observation is saying that for a given photosensitive material, there exists a certain cutoff frequency of the incident radiation, and that is called threshold frequency, below which no emission of radiation will occur. Okay, no matter how intense your light it be. Okay, so above threshold frequency, the stopping potential, or equivalently the maximum kinetic energy emitted photoelectrons, increases linearly with frequency of the incident radiation but independent of intensity. You can see here, see in this figure, I hope it is visible to you. See, this is the stopping potential. Since I have shown in the previous class, I am not highlighting so much, I'm just recapping these facts. See, the stopping potential is increasing in this direction as you increase the frequency, so incident like frequency of the incident radiation and stopping potential, they are actually proportional. Okay, this is the incident frequency. And see, look, this is actually called threshold frequency. Until this frequency reaches a particular value nu zero, which is called threshold frequency, you won't get any stopping potential. Sorry, you won't get any photoelectric effect. So until and unless you reach up to this minimum frequency, okay, you are not going to get photoelectric effect. So this is actually called sorry, this is called threshold frequency. and and then the fourth one is actually, see, photoelectric effect. As soon as you shine a photosensitive material, you would likely to be getting the current in the circuit. That means as soon as you irradiate the metal surface, immediately electrons comes out. So this is called instantaneous phenomena. And okay, this actually this will be 10 to the power minus 9 second. Okay, almost 10 to the power 10 to 10 to the power 9. Okay, 10 to the power 10 minus 10 to 10 to the power minus 10 second it takes to come out. So electrons to see, this is, that means, like this time is very small time, right? So photoelectric effect happens within this much fraction of times. So that's why it is incident phenomena. Sorry, it is called instantaneous phenomenon. Okay, instantaneous phenomenon. So these are the more major four four major observations which we'll see wave theory would not be able to explain properly, whereas Einstein's quantum theory of radiation could be able to explain all these four phenomena. Okay, let us first see what are the failures. What are the failures? See, first one is energy depends on amplitude of the wave, not or intensity, but it does not depend on frequency. See, look what happens. According to wave theory, so according to wave theory, we know. See, I can write. See, light vector is light generally denoted by electric vector. So I am writing electric vector only. Electric vector can be expressed in terms of sine omega t minus kx or something. So where you can see this E0 is called the amplitude of the wave. Amplitude, okay, amplitude. So when this is the amplitude, what is the corresponding energy? The corresponding energy density will be half epsilon naught. This is called electric energy density, half epsilon naught E0 square. That means you look in by the, like, according to wave theory of light or radiation, electromagnetic radiation, the energy actually depends on the amplitude. It does not depend on the frequency omega. Okay, it does not depend on the frequency. So then what happens? According to this wave theory, as much as, like, as you increase the intensity, the metal electrons which are actually subjected to that increased intensity, they should acquire more and more energy, because you look, this intensity, again, intensity is directly proportional to the amplitude square. Amplitude square. And also we look here, the energy density, that is also directly proportional to amplitude square. Amplitude square. Amplitude square. Okay, that means U is directly proportional to I, that is the energy density of the elect electric vector here, the energy density of the incident radiation is directly proportional to the intensity of the light. So if this intensity increases, what would happen? Electrons, which are subjected to this kind of radiation, they will absorb more and more energy, and hence what we expect, we should expect that the emitted electron should have more energy. Okay, more energy, more kinetic energy. So what does this imply? If you have more kinetic energy, look, if you have more kinetic energy, this kinetic energy, okay, I'll not write maximum. See, the kinetic energy, in fact, maximum kinetic energy is actually corresponds to the stopping potential. Stopping potential. Okay, stopping potential. That means, see, according to wave theory, what is happening? This is proportional to this. So, if intensity is increasing, what would happen? So, U also will increasing, and then what should increase? Kmax. If Kmax increases, then what it implies? It implies that stopping potential, stopping potential also should increase. Okay, but what we have seen? We have seen that stopping potential does not depend on the intensity of the incident radiation. So I hope you have understood what is the ambiguity in this wave theory. So according to wave theory, as we increase the intensity, we increase the energy density of the wave or the radiation. So electrons which are emitted up, or photoelectrons which are coming out due to this radiation should have maximum kinetic energy. More and more kinetic energy they should have. That means if you increase the intensity, then your stopping potential also should increase. But we have seen, even though the saturation current depends on the intensity, but stopping potential does not depend on the intensity. Does not depend on the intensity. That means, this is failing. So wave theory is failing to explain the independent nature of the stopping potential with intensity. Another point is, see, we have seen if we plot, we have seen if we plot frequency with stopping potential, what we have seen? We see that frequency, the stopping potential actually increasing linearly, and not only that, see, for two different material A and B, what you have seen, until you reach, or until you radiate the metal A at least with this much radiation, nu 01, or in this case suppose nu 02, so there will be no photoelectric effect. So wave theory could not explain both the stopping potential and also the existence of threshold frequency. Wave theory fails to explain the threshold frequency also, existence of threshold frequency. Okay, now we'll see another difficulty. So in this case, whatever intensity you may take, you can take you. So whatever intensity you like, if you may not be able to get photoelectric effect unless you use light having a certain cutoff frequency. Okay, so that is the threshold frequency. Now, the third fact is this instantaneous nature of the photoelectric effect. Okay, so what does this mean? So this means instantaneous, as you have seen, photoelectric effect actually happening within 10 to the power, sorry, 10 to the power minus 10 to 10 to the power minus 9 second within this fraction of time. So that's why it is very, this is very much instantaneous. That means as soon as you shine the metal surface with light, you will be able to get the photocurrent. But what happens according to wave theory? Look, wave theory, if you see like this, it goes, okay? As it advances like this, you look at this. See, we have seen the intensity, sorry, the energy depends on the amplitude. So each point, actually energy, in a complete wave, the energy is actually uniformly distributed all over the space. So suppose I have some electron over here, okay, in the medium, in the metal surface, which is actually interacting with, like intersecting the wave at this particular position. So this will actually would would have no energy here. So you can see these two positions. So they will actually, the electrons will be individual electrons, because see, the energy is spread over a space. Since it is wave, energy is spread over a region of space. So if you have electrons all over, so individual electron will actually acquire individual amount of energy, and that's how, if there are more electrons, so they will be actually equally, the energy will be equally distributed over a space, and hence for a particular electron there may be, for a particular electron there may be having energy not very sufficient to overcome the work function. Okay, I'll repeat it. See, since according to wave theory, wave is spread over a space, and the energy also is actually distributed over the space. So at a single time, energy is actually supplied to many electrons. So what happens? Each electron actually absorbs some amounts of, or different amounts of energy. For some cases, some electron may have enough energy to overcome the work function. Okay, work function. Sorry, yeah, energy absorbed by electron. Okay. Oh, sorry, I should write energy. Some electron have greater energy absorbed is greater than work function. Okay, but so photoelectric effect will happen, but to absorb sufficient energy to overcome this work function, according to wave theory, since energy is spreaded like this, it will take hours or more than that, hours or more than that. Okay, more than that. So if electrons has to electrons have to absorb energy from the wave, and then they will emit from the metal surface to acquire the sufficient amount of energy for an electron from the wave to overcome the work function will be very very large, and that is like more than hours sometime. But what we have seen we have seen that photoelectric effect is actually an instantaneous phenomena. It occurs immediately. Okay, so this is what was the limitation. Like these are the 3 points of limitations of classical wave theory of electromagnetism. Now we'll just learn how Einstein actually explained the observations of the photoelectric effect in the light of quantum theory of electromagnetic wave or radiation. So in 1905, Einstein explained photoelectric effect on the basis of Planck's quantum. See, 1905, it was 1905, based on Planck's quantum theory, which is which states that light radiation travels in the form of discrete energy. Light light radiation travels travels light radiation travels in the form of discrete unit or pockets of energy, in the form of pockets of energy which are called, and these discrete units or pockets are called photons. Okay, photon. So 1905, based on Planck's quantum theory, which states that light radiation travels in the form of discrete units or pockets of energy. These discrete units or pockets are called photons. Okay, so based on Planck's quantum theory, Einstein was able to explain the photoelectric effect, phenomena of photoelectric effect. So I'll just elaborate on this. Look, what has Einstein changed? Like what was the change in the idea? So earlier it was wave. So wave has nature, energy, and then wavelength, etc. Now he is saying that wave is actually, sorry, radiation or electromagnetic radiation, I will say EM radiation. EM radiation, it actually, when interacts with the matter, it behaves as a particle, and you know that particle has energy. EM radiation has energy. I'm sorry, that just a minute. EM radiation behave as particle which are called photon of photon, which are called photon. Okay, and each photon is having energy E is equal to h nu. What is this nu? Nu is the frequency of the radiation. Frequency of radiation. And what is this? This is Planck constant. Okay, this is called Planck constant. Okay, so what Einstein had told, Einstein had proposed that the radiation which is actually irradiating the metal surface behaves as photon having energy h nu, where nu is the frequency of particular light and h is the Planck constant. Since this is constant, so energy directly depends on frequency. So according to Einstein's idea of photoelectric effect, energy depends on h nu. So I'll write it here. Energy depends on h nu. Nu is the frequency. It implies that E is directly proportional to nu. Okay. All right. So this is what the thing. And now look. Now according to Einstein's this idea, see the photons are coming, and since photons are acting as particle or a pocket of energy, as you can see, these are pockets of energy. Pockets of energy, and each having energy h nu. Each photon, this also has h nu, this also has h nu energy. Okay, since as long as their frequency is same, the energy would be the same. So look, these energy pockets, when they interact with the matter, they act as particle, and at a time only one electron can be encountered by, or one electron encounters only one photon at a time, as you can see from here. At a time only one electron will be imparted energy through collision, elastic collision. So these photons, which are acting as particle while interacting with the metal surface, electrons of the metal surface. So what is happening? These photons are having energy, okay, energy. So they will transfer the energy to the free electrons on the metal surface, through collision, elastic collision. So when collision happens with the photon, and this is photon, suppose, with the photon and the electron, the energy of the photon will be imparted to this electron, and with that energy, if that energy is sufficient in the sense, if that energy, suppose h nu, is greater than this, then, so if the energy of the incident radiation is greater than what function, then what happens? Then what happens? Then the energy of the photon will be will be utilized in two ways by the electron. So up to now, what we have learned, so incident photon, they are actually kind of particles when they interact with the metal surface with the electron. So as you know, only one electron can knock out only one electron at a time. So what happens when energy, high energy photons, this h nu, so energy of the photon depends on nu only, not on the wavelength. So as soon as you see there is energy h nu is actually transferred to the electron, and this energy will be actually spent by two ways if h nu is greater than w0, then then sum of its energy, that means h nu will be spent to overcome spent to enable an electron to overcome the work function, overcome this. And if the energy is, and okay, so if the energy is this, then sum of its energy of h nu will be spent to enable an electron to overcome this. And second thing is the rest of the energy of the photon will be imparting kinetic energy to the electrons. Kinetic energy to the electrons. Okay. So rest of the energy will be imparted to increase kinetic energy of the emitted electrons. Okay, I'll write in terms of mathematics. See here, it is already written. See, like according to conservation of energy, what we know, initial and final energy has to be the same. Okay, so look here, the h nu is actually spent in two ways. What is that? One is it is giving the maximum kinetic energy, and it is supplying the work function. Okay, so k max will be okay. So this is actually famous Einstein's equation. So what does this mean? If you irradiate a metal surface with frequency nu, so each photon has energy h nu, and they will interact at a time with only one electron, and they will immediately transfer the energy to the electron. And see, that energy will be spent in two ways: to increase the kinetic energy and to overcome the work function. Okay, work function W. So look this. See, if this becomes h nu becomes this, so we can write like this anyway. So what does this mean? So when the energy of the incident photon becomes exactly equal to the work function, then electrons will not be having any kinetic energy. So kmax will be 0 in this case. Okay, if the incident light has frequency exactly equal to the work function, then there will be no kinetic energy of the emitted electrons. Whereas when your frequency has energy greater energy, then the energy part of that energy will be used to overcome the work function, and the rest of the energy will be used as or converted into the kinetic energy of the emitted electrons, photoelectrons. Okay, so this is the famous, so K max, this is actually the famous equation, h nu minus w0, or we have written with potential also. So, sorry, this is h nu or h nu 0 I can write. So this is the threshold energy, or this is corresponding to threshold frequency. Okay, so we can see that. So this K max will be equal to h into nu minus nu 0. So this is the maximum kinetic energy an electron can have, okay, which are emitted by a certain photoelectric effect, okay, from certain metal surface. So nu 0, nu 0 actually corresponds to work function, that you should remember. Okay, so this is the famous equation. So these are two equations. Actually, I'll write Einstein's photoelectric emissions equations for that. Those are actually h nu, the energy of the incident photon, and work function. I'll write. So this is the maximum kinetic energy of incident photon. I'm sorry, this is not incident photon. Kinetic energy, maximum kinetic energy of the emitted electron, and this is the energy of incident photon, energy of the incident radiation. Okay, and this is the work function. Okay, so from here we can see, we'll try to explain all the observations what we have seen with this particular equation, and in fact we can actually write this equations in terms of this also, h into h minus, sorry, h into nu minus nu 0. This is equal to k max. Okay, this is also another form of Einstein's equation. Now we'll take up one by one what are the observations and how we can explain those. See, first let us take this observation. For a given photon sensitive, so I'll write Einstein's equations here. See, according to Einstein's equations of photoelectric effect, K max, maximum kinetic energy of the emitted electrons, will be equal to the energy of the incident photon minus the energy which is related to the metal surface, which is called work function. Okay, now look, for a photosensitive material, given photosensitive material and frequency, that means this is fixed and this is also fixed. So incident radiation, okay, fine. The photoelectric current is directly proportional to the intensity of the incident radiation. Okay, so look, what does this mean? I'm sorry, we should go with this. Okay, look, in this case, what is, we have to understand, according to quantum theory of radiation, what is intensity of light. Of light according to quantum theory of radiation. I'll tell it here. See, intensity, look, since this actually photons are thought of, suppose this is a metal surface, you have electrons, free electrons like this, okay, free electrons like this. And see, we have assumed that the see, radiation is actually some kind of photon or some kind of particle, and at a time one particle can interact with a single electron only. Okay, so if I have, suppose initially I have some 10 photons. Okay, 10 photons can interact with only 10 electrons, or here I have drawn 2, so it can emit actually 2 electrons here and here. Okay, but if suppose I have 50 such photons per unit area, they can interact with 50 different electrons, and all 50 can be emitted. Okay, if the light radiation is of suitable frequency or suitable energy, then see, since photon is having particle nature when interacting with matter, then each photon will actually interact with only one electron or at a time. So if your photon per unit area and per unit time increases, that would give rise to greater photoelectric current. And you know what is intensity? According to quantum theory, it is the number of photons per unit area or in a given unit area per unit time. Number of photons, okay? So what is that? So this actually number of photons, okay, number of photons per unit area, suppose, and per unit time, per unit time. As I have given you the explanation that each photon will be interacting with only one electron. So if you have number of photons or number of, yeah, number of photons per unit area per unit time, then number of electrons emitted also will be increasing. Okay, with the increase in intensity. So that's why if your number of photons increases, then number of emitted electrons also will be increasing. So you get, see, current is actually q by t. If the number of charge is more, then this is time. So this will give rise to photocurrent, more photocurrent, because you know your photons are actually bombarding more electrons as you increase intensity. Okay, this part is over. Now let us see how the stopping potential. So from Einstein's equation, how we can calculate or how we can explain this. Let us see. See, in this case, as I have already told, in quantum theory, energy does not depend on. So energy depends only on the frequency, but does not depend on. Okay, does not. It does not depend on intensity. So as you have seen that the energy of the, according to quantum theory or Einstein's idea, quantum idea of photoelectric effect, that each photon has energy h nu, and suppose that energy is not changed, only the intensity changes. That means intensity changes means you are actually ejecting more photoelectrons rather than having greater kinetic energy of the electrons. Okay, and see, stopping potential, we have seen, we have discussed the stopping potential energy is actually directly corresponds to maximum kinetic energy of the so maximum kinetic energy is directly proportional to stopping potential, and that can be increased only when you increase the frequency, not by increasing intensity. And you have seen if intensity increases, more number of photon will be emitted, so you will get more saturation current, but you will not have different stopping potential. If all the intensities are having same frequency, then you have the same stopping potential. So from here you can explain that also. Okay, stopping potential. So since energy depends on frequency according to quantum theory, stopping potential also will be varying with frequency rather than varying with intensity. You can see that. See, the stopping potential is actually linearly varying with the frequency, not with the intensity. Okay, and also threshold frequency, how it could explain about threshold frequency. See, even if you have very large intensity, but you may not be able to get photoelectric effect, because see, according to Einstein, this is Einstein's equation of photoelectric effect. Look, this is the actual work function, okay, work function. And see, as we know, energy depends on frequency. Okay, for various metals, they have different values of this work function being the restraining force which is given by the nucleus or the metal surface. So to overcome that, you need to provide an electron a minimum amount of energy for a particular metal surface, that is called work function. And see, since according to quantum theory of radiation, energy depends only on the frequency, not on the intensity, you should have a cutoff frequency which, see, cutoff frequency in the sense, see, you should have energy either equal to work function such that electron just leave the metal surface, or you should have energy greater than, so your photon should have energy greater than work function. Okay, or at least equal to this work function. So this is actually corresponding to threshold frequency. Okay, so this explains, so you can see this explains also what is, how threshold frequency exists for various metals. Okay, and the last part, that is this one, the photoelectric emission is instantaneous process. See what I have told, that according to quantum theory or according to Einstein's idea of photoelectric effect, so in the metal surface you have free electrons like this. Okay, they are treated as particle. They are treated as particle, and see photons, according to Einstein or according to Planck's theory or Planck's quantum idea, that radiation, electromagnetic radiations are not just wave, they behave as particle or discrete unit of radiation having energy h nu, and when they interact with matter, actually they behave like a particle. Okay, and see, when they interact with this metal surface, the electrons of the metal surface, what happens, actually there would be elastic collision, and at a time only a single electron, so this is the elastic collision happens between photon and electron, and and the transfer of energy is a single short process. This is a single short process. Since it is an elastic collision, between photon and electron. So the energy transfer, the process of energy transfer is a single short process rather than a continuous process. As we have seen in case of wave theory, in case of wave nature of light, the energy is spread over space, and per unit time, a single electron can absorb a certain amount of energy that may not be sufficient to overcome the work function. That's why to gain a sufficient amount of energy to overcome work function, it has to absorb energy continuously for some hours. But in this case, if you have a suitable frequency, light of suitable frequency or with threshold frequency also, so photon and electron they interact and the energy of the photon is transferred to the electron at a single collision or single short process immediately. Okay, and that's how the photoelectrons emits from the metal surface within almost 10 to the power 10 second to 10 to the power minus 9 second. So which is actually very less fraction of time, within a very less fraction of time. So that's why it is actually instantaneous phenomenon. So we can see how Einstein could explain all the observations, experimental observations of photoelectric effect. So, so his famous equation. So we can see famous equation photoelectric famous equation on photoelectric effect is given by this: K max is equal to H nu minus W0, that is work function. Okay, work function, right? So this can be actually written in terms of stopping potential EV0. Okay, and this can be written like this only. So now if you divide this with E, look now if you plot stopping potential V0 versus new frequency curve, how you get? So curve will look like this, and it will actually intercept here somewhere, which gives you this minus W0 by E, and this frequency will be the new zero. Okay, and you can see the slope of this curve. Okay, slope of this curve will actually give you, see, the slope of this curve will give you the Planck constant. So the slope will be this. Okay, so from, see, by plotting V0 stopping potential versus frequency, you can get a curve like this, which is linearly increasing. Like stopping potential will be increasing linearly with the frequency, incident frequency, and it its slope of that curve will give you or enable you to find out the Planck constant. Okay, like this. Okay, all right. See, with this we can see that light is not only a wave, it acts as a discrete unit, which is actually called photon. And this photons has not only energy h nu. Einstein had showed that it has momentum also. Momentum, which is given by E by C, or h nu by C, and nu by C will be actually lambda. So C is equal to nu lambda. So nu by C will be 1 by lambda. So A is by lambda. Okay. So so see, anything which has energy and momentum, these two quantities are actually corresponding to particle nature of photon. Particle nature of photon. Particle nature of photon. Particle nature of radiation. I'll just repeat this idea. See, Einstein could explain the photoelectric effect by considering or by taking the idea of Planck's that radiation actually is composed of discrete units or pockets of energy, and those pockets are called, or discrete units are called, photons, and each photon has energy h nu, and he showed that each photon has momentum also, that is E by c. C is the speed of light and E is the energy of the incident photon, which is h nu. So if you just convert it like nu by c, it will be actually 1 by lambda. So I have written h by lambda. Okay. So this, we'll be learning in the next section, de-Broglie's hypothesis, etc., that radiation has a particle nature, and in conversely, particle also will be having wave nature, and this equation will be actually the bridge equation, between the wave nature and particle nature. So, and this is actually the bridge. The Planck constant is actually acting as the bridge. Okay, so that we'll learn. And now look, I'll just give you a few properties of photons, and then I'll stop it. Okay, the properties of photons. So in the interaction of radiation and matter, radiation behaves as if it is made of particles called photons. And see, photons are neutral neutral particle. Okay. Then second is they have energy. So photons have energy is equal to h Planck constant times the frequency of the particular radiation, and momentum 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 p is equal to, momentum p is equal to E by c. Then third is all photons of, see, if you have a particular frequency, they corresponds to same energy. Like whatever photons you may have many photons of frequency nu, then they will correspond to energy h nu, and obviously they will have the same momentum also. Okay, same momentum. And photons are electrically, okay, I have told you that. So in a particular interaction, the total energy may be constant, total energy and momentum will be conserved, but the number of photons may not be conserved, may not be conserved conserved in interaction. Okay, interaction, during interaction, I'll write during interaction with matter. Okay, during interaction with matter. Okay, and then the last one is actually, if you increase the intensity, that means what is that you are doing. If you are increasing intensity, so increasing intensity means increasing intensity, increasing intensity of radiation means of radiation means increasing increasing the number of number of photons per unit area per unit time. Okay, so with this I'll stop it here. We'll next day what we'll do, we'll just see the de-Broglie's hypothesis and matter wave related things we'll see, and we'll take up few numerical examples related to this particular topic, like dual nature of radiation and matter. Okay, and probably we'll try to finish that topic up. Okay, all right, so thank you for your patience. Deepa, if you have any specific question you can ask me, or else we'll stop it here for today. Do you have any question? Okay, then we'll stop it here for today. We'll meet again on Wednesday. So bye for today.